Before going back to material, just a reminder that the second midterm exam is a week from today in class, the usual thing, 30 multiple choice questions, bring a pencil, what else? I encourage you to take as many of the old exams, midterm 2s, as you can. Midterm 2 will cover the material primarily from the end of after the first midterm. So starting with carousels and roller coasters and up until what we get through this week, which will be somewhere in the flow of air around balls. So balls and air. And what else? Stuff from the first midterm is fair game to a modest extent. And in part that's because physics builds on itself, and so it will be hard, it's hard to disentangle and like not talk about momentum when momentum shows up in so many other things. So yeah, it was part of bumper cars, but it's still here. Any questions about midterm exam 2 issues? All right. The only problem set was the one that was just due. Problem set 5, there's no 6th problem set for right now anyhow. So where things are at present, I'm trying to take you through water distribution and just to remind you what this, to rebuild the stage here. The story of water distribution is a context in which we can sort of look at the simplest ways in which fluids can flow. And the simplest story, to try and make things as simple as possible, are to look for water flow through stationary plumbing, where that water is flowing steadily along and it has no swirling motions in it. Basically, the issue is this, that fluids are complicated. They have motions, all kinds of motions. The equations describing their motions remain, to a large extent, unsolved problems in mathematics. They're really hard to solve in all their gory detail. So you have to make approximations or simplifications. And we're making the biggest simplifications to start with. The biggest simplifications are to say that the plumbing itself that we're paying attention to doesn't move around. And therefore, there's no energy being added or subtracted from the flow. You're not doing work on it by pushing on it with the plumbing as it moves in the direction of the push. And so that's first simplification. Keep everything, all the environment stationary. Second simplification, ignore all the rubbing effects that influence fluids, much as the rubbing effects influence the motion of objects, solid objects. They experience frictions, right? Well, there are friction equivalents and worse in the world of fluids. So we're setting those aside too. And one of the key ways in which we set those aside is we get rid of a concept known as viscosity. It'll show up later today. But viscosity is the syrupiness of fluids. Even air has viscosity. It's a little bit syrupy, not very much, but certainly something like maple syrup or molasses or tar. These are very seriously viscous fluids. They have a lot of interaction with themselves, sort of internal friction. And the third thing that we're setting aside is the possibility that the flow has trouble keeping itself organized and begins to tumble, what's known as turbulence. And you've experienced turbulence, the commonplace would be on an airplane ride. Fluids don't always flow smoothly, and that's another thing we're setting aside. So, in the world of, super simplified world, the structure isn't moving, the flow isn't rubbing on anything, no friction effects, no turbulent effects. And a last one to add is we don't start and stop the flow today, or at least in the water flow here. Let it go and reach what's called steady state. And in that very sort of maybe oversimplified world, you can describe things very cleanly. The relationships all become very simple. And fortunately, a lot of not perfect situations where, there is some viscosity in the fluid, and things aren't exactly steady, and not everything's completely motionless around. Even in those contexts, you can still use this. It's pretty good. So it gives you a lot of insight into how fluids, it should give you a lot of insight into how fluids flow. All right, so that's the stage. And where we are at present is that in that limited environment, where the fluid is flowing steadily through a stationary environment and no tumbling, It has streamlines. That situation is known as steady state flow. Pretty sensible name for it. And in that context, the fluid has what are known as streamlines. That is, if you start with a fluid upstream and you follow a drop of fluid as it moves through the system, it traces out a path that you could imagine highlighting through the system in a photograph. That highlight mark is the streamline, and every drop that follows that path is indistinguishable. They're distinguished only in when they went through. One went through now, one went through now. Those two drops, separated by a few seconds, are otherwise identical. They have the same energy per drop. They follow all the same features, and so you know a lot about what each drop is doing as it goes through the system. The main thing you know is that its energy, the amount of energy in that drop, where drop is just my jargon, or my expression for a specific volume of water. So the energy per drop, energy per volume of water, is constant along that streamline. You can't be sure that it's constant between two different streamlines. They have different histories. The drops on this streamline and the drops on this streamline have different histories, and we don't know whether out of view upstream somebody added extra energy to the drop on top. So all those drops. So that streamline has more energy than this streamline. We don't know that. But what we do know is that along a single streamline, life is simple. They all have the same energy, all the drops, all the way along that streamline. And all they can do then is exchange their energy between three different forms. Pressure potential energy, which I talked about last time. Gravitational potential energy, which is an old friend or enemy or whatever, frenemy. And kinetic energy, which is yet another thing we've seen before. Those three forms of energy, pressure potential energy, gravitational potential energy, and kinetic energy, the drops can trade. They can exchange energy between those forms. But the sum of the three is constant. Questions about that idea, those ideas, or anything that's come up yet? Where I really left off last time was in showing you the ways in which the energy could be I would say forced, caused to shift from one form to another. It's not arbitrary. It doesn't happen just because the drop is heading along and decides, at this point in the pipe, I'm going to convert my gravitational potential energy into kinetic energy. It's not up to the drop. It's the environment that causes these changes. And we can make them happen by changing the environment. And there are 6 ways in which energy can be converted from one form to another, because you've got 3 things, convert one, take them in pairs, convert one into the other. There's 6 possible directions you can make the conversion. And I was working my way through the first pair last time when the hour ended. The first pair is basically the idea that how do you make the water exchange pressure potential energy for gravitational potential energy, or vice versa? How do you cause that to happen? Well, the first thing you do in making that exchange occur is you don't allow the water to speed up or slow down. In other words, you make sure that the water keeps its kinetic energy constant. Same speed, therefore same kinetic energy. So don't let it change speeds, but to force it to convert pressure to gravitational, gravitation to pressure, you go up and down. And the way you go up and down is you send the water through a pipe that's vertical, or partly vertical, that has some rise in altitude or descent in altitude. When you do that, if you send it through a pipe that has a constant cross-section, so you slice the pipe open at various places along its path, and the pipe is the same, looks the same. It's 1 inch in diameter everywhere. It doesn't get wider or narrower. If you do that, you change the speed. Go constant. The water has to move at constant speed through a pipe that's got a constant cross-section. And the reason for this, now that I have a little time to talk about it, is water is an incompressible. I told you that fluids are incompressible. You can't change their density much. Squeeze them all you like. Water has a density of about a 1,000 kilograms per cubic meter, also known as a metric ton per cubic meter. You can't change that much. Tiny, tiny bits. But otherwise, you can squeeze it, unsqueeze it, doesn't matter. It's always going to have that same density. And the a consequence of that is if you put the water in to a pipe faster than you take it out of the end of the pipe, and the pipe has got a constant cross-section, it's piling up somewhere in the pipe. You're accumulating it there. It's going in faster than it's coming out. How's that possible? It will have what I think of as a traffic jam. It's like, it's like bumper-to-bumper traffic. Bumper-to-bumper traffic on a road is an incompressible fluid. If it's not bumper-to-bumper, people can pack more tightly or unpack. But if it's bumper-to-bumper, every patch of roadway is occupied by a car, you can't add extra cars to that roadway. They're moving, but you can't pack in twice as many cars in that roadway. That's over bumper-bumper, it's traffic jam. Similarly, if you spread them out, they'll not be bumper-to-bumper anymore. You've got vacancies in there. So if the flow of cars on a road is bumper-to-bumper and going, and the road is uniform, 12 lanes the whole way from here to DC. People would dream of this, right? Wow, vacation, we get home. Except it's bumper-to-bumper traffic. Sorry, it's not good anyway. So if it's 12 lanes wide, and it's bumper-to-bumper, the cars better be entering the roadway at the same rate they're leaving the roadway. If you're putting twice as many cars in per second at the start than you take off at the end, they're piling up. Or you do the reverse. You take them off twice as fast as you put them on. They're making gaps. Questions about that idea? Where's this relevant? This is the same with water. You put water in at 1 gallon. Let's do it with speed. You put the water in at 1 foot per second. Now I'm in English units or American units. 1 foot per second into a pipe of uniform diameter. You better be taking them out the other end at 1 foot per second. Otherwise, traffic jams or vacancies. So, in a uniform pipe, the speed is fixed. Therefore, the kinetic energy is fixed. The water can't play with that. What it can play with is its gravitational and pressure. And as the water goes up a pipe, it's clearly accumulating more gravitational potential energy. It's higher. If you took it out of the pipe and let it fall, it could do things that it wasn't able to do before by virtue of its gravitational potential energy. So it must be using up some other form of energy because energy is conserved. Its pressure is decreasing. So water that's rising in a uniform pipe is losing pressure. All right? Hopefully these are sort of at least somewhat familiar in everyday life. The higher you go in a very simply plumbed building, the lower the water pressure is. You open the faucet on the 7th floor of a simple building, and the water comes dribbling out. You try to block it, it's easy to block. Not much pressure in it. Go to the basement or the ground floor and do the same thing. The water, first of all, is coming out faster, which is a second transformation. That's a transformation obviously into kinetic energy. But if you try to stop that water flow, it's a lot harder to stop down low. The pressure's higher. Similarly, let the water descend through a uniform pipe. It gives up gravitational potential energy, but it accumulates pressure potential energy. And this, just to bring up a practical issue, this is one of the concepts behind water towers, which is in the book, and sometimes I remember to talk about it in class, other times not. Water towers store two things. They store water, and they store energy. And the energy is actually a major important part of what it stores. You put the water tower up as high to begin with. First off, you put the water tower on a hill if you can, and then you build it up to some height even above the hill. When you put water up there, it has a lot of gravitational potential energy, even when it's motionless, no kinetic. It has atmospheric pressure at the top of the water in that tower because it's just sort of open to the air. So there's no usable pressure potential energy. So no kinetic, no pressure. Lots of gravitational potential energy. And if you start to consume that water, you let it descend through a pipe. It's got a pipe at the bottom of the water tower, right? The pipe comes down, and as the water descends through that pipe in anything resembling a steady state flow, it will convert its gravitational potential energy into kinetic energy. Into pressure potential energy. Did I say that right? Or I let my mouth talk without my head guiding. It converts gravitational potential energy into pressure potential energy on its way down. So now you've got high pressure water at the bottom of the water tower, which you can do whatever you want with that. Lots of energy in the form of pressure potential energy. All right? Yeah, Liam? What makes pressure potential energy different from kinetic energy? The pressure potential energy is, even if the water is not moving, and therefore it clearly has no kinetic, the fact that it is at high pressure and there's a promise to replace it if you use it, it has lots of energy, it can do things. It can, for example, it can convert that into kinetic energy if it goes through a nozzle, which we'll come to in a minute. That the nozzles force water to convert pressure potential energy into kinetic energy. Okay? Other questions? All right, so the descending water out of a water tower, it quickly develops a lot of pressure, and as it's delivered to your house, pressure and volume, the product of the pressure in the water times the volume of water that's delivered, that's work, or that's energy. That's the energy being delivered. So the water descending out of the water tower converts its gravitational potential energy into useful forms that does things. Okay? Yeah, David. Okay, so its speed can't change. Why doesn't it accelerate due to gravity? It can't accelerate due to gravity because that would mean that as you go down the pipe, it's traveling faster and faster downward. It's violating my rule that, and I don't have any choice in this rule, that the water can't speed up on its path down. If it did, it would leave gaps behind it because every drop occupies a certain volume. And if you start with them all packed up tight together at the top, and you get halfway down, they're traveling fast, much faster than they were before, they will have had to spread out. It's like cars speeding up on the highway. Yeah, it's bumper to bumper at the start of the highway, but if they are speeding up, there are now gaps between them. And water won't let that happen. The water won't actually sort of pull apart into water and empty space, because there's no air there either, so the empty space is really empty. Is that okay? So this conversion, the uniform pipe forces constant speed and therefore constant potential kinetic energy. Think before I speak. Okay, you'll see that there are ways in which water can descend and speed up, but it's not in a uniform pipe. If you want the water to exchange its gravitational potential energy with kinetic energy, so let's leave pressure potential energy stuck. In the first story, that first slide, we forced kinetic energy to be constant. How? By using a uniform pipe. Now we're going to force pressure to be constant. How? By doing all the action up and down in the open air, where the pressure is atmospheric pressure. So if you make water rise in the open air, you shoot it up with a fountain nozzle. Let's not pay attention to the fountain nozzle itself yet. Let's just look at the water above the nozzle. You've seen fountains before. The water shoots way up in the air, or a hose, anything you like that just shoots the water up. Once it leaves the nozzle, which is not part of this particular story, the water is exposed to the open air. Its pressure, at least at its surface, has to be atmospheric if it's in steady state flow. Briefly, it can be higher or lower than atmospheric pressure, but if it is, there's going to be acceleration right at that surface, because that surface is going to be experiencing a difference in pressure imbalance. So the water rising, shooting up in the air from a fountain, it's at atmospheric pressure. Water falling down a waterfall is at atmospheric pressure. Okay? Those two cases, water rising in a fountain or descending in a waterfall, their pressure is fixed, therefore pressure potential energy is fixed, but that doesn't mean that the other two forms of energy aren't interchanging. They are. As the water is rising in a vertical fountain, or a roughly vertical fountain, it is losing speed. It's a falling object, right? It's losing speed on its way up. You've seen this way too many times. And so it is losing speed with that kinetic energy. And where's the energy going? It's going into gravitational potential energy. So the water rises until basically all the energy, if you shoot it straight up, it comes to a stop briefly, which is a little iffy because in steady state flow, you can't have the water actually stop completely. It's got to keep on moving, otherwise it piles up. But okay, so the water goes up, and so these are slight oversimplifications. You should be slightly aware of that. What does it matter? Not a lot. The water, in its process of rising, is basically losing all of its kinetic energy. Its pressure potential energy is as low as it can be. It's at atmospheric pressure. So the water goes up as high as it possibly can. That's when all of its available energy, the energy that we've been talking about here, is in the form of gravitational potential. That's what limits its height, basically. It turns all of its energy per drop into gravitational potential. How high can it go? That's where it is. That's where it peaks. And on the way down, or down a waterfall, it's the reverse. The water starts with a lot of gravitational potential, and it loses that. And because it's in the open air, its pressure potential energy can't change any more than its pressure can change. So it converts its gravitational potential energy into kinetic. It goes faster and faster and faster. And for it to go faster and faster, actually, here now I can talk about David's question about why the water can't speed up or slow down. On the way up, as it slows down, it is packing more tightly together. At least at every altitude, there's more water, because the water was traveling fast down low and slow up high. There must be more water in each sort of 1 foot interval. The higher you go, the more the water is there. How does it do that? It spreads out. It gets wider. The flow of the water gets wider as you go higher in a fountain. It starts as a narrow jet, and then the jet gets wide, because the water is accumulating at each height interval, but it's got freedom to spread out, and that allows you to have more. It's like in the car analogy. It's like the roadway started as a 1-lane highway at super fast. You have to enter at 100 miles an hour, but then the highway widens out through 2 lanes, 3 lanes, 5 lanes, 10 lanes, and the cars spread out, slow down, and things can still be steady. Yeah, they come in really fast through a narrow opening, and then they spread out. Do you follow that? Keep beating on it. I think I'll stop. On the way down, it's the reverse. As water goes over a waterfall, and you've seen this too, the water starts slowly, and then as it speeds up, it gets narrower. Why? Because it's traveling faster. You've got less water at every height interval, because it zooms through there faster, so it gets narrower. So when you pour water out of a container, it starts wide at the top, and then it narrows as it goes farther down and it's traveling faster. All right? All these things, I hope it makes some sense to you now. Watch the water rising and falling from fountains and waterfalls, and when you pour water out, and watch its speed changes, and therefore its width changes. All right. Third pair of energy exchanges. I've showed you, if you keep the speed constant, that was the pipes, of constant pipes. I showed you keeping the pressure constant. That was when you've got a waterfall or a fountain, as the sort of extreme examples. And now let's keep the gravitational potential constant. Work on a horizontal surface, or work on a horizontal region. Now we want to convert pressure potential energy to kinetic energy, and kinetic energy to pressure potential energy. We're keeping gravitational fixed by not going up or down. Well, you can force water to convert its pressure potential energy into kinetic energy with a nozzle. What a nozzle is a pipe that gets narrower. And since water is incompressible, you can't pack it any tighter than it already is. If the water enters the pipe, in the wide area of the pipe, traveling a certain speed, and you have to let it then continue through the pipe, and the pipe gets narrower, the water has to speed up to get through that narrowing without causing a traffic jam behind it. This, in the roadway analogy, is like when you've got a construction or an accident or something like that, and the 10-lane road is down to 1 lane. Everybody's crawling along in the 10 lanes leading up to that 1 lane. they go fast through the narrow one lane, assuming they're not rubbernecking, and then they go out the end and do other things. Okay? So the speed has to increase as they go through the narrow part. Can you follow that idea, or any questions about the need for speed in the narrowing? So that happens in a nozzle, that the flow of water speeds up there. Where does the energy come from? To create that higher speed means more kinetic energy. Where does the energy come from? It comes out of the pressure. So the water actually does accelerate forward into that narrowing. It's pushed forward by a pressure imbalance. There's high pressure as it's struggling to get through the wide part of the pipe slowly. And then as it goes through the narrow part, it's pushed forward because it's being pushed into low pressure, high speed in the nozzle itself, in the tip of the nozzle. It has converted its pressure potential energy to kinetic energy. It blasts through that narrowing, having converted essentially all of its available pressure potential energy into kinetic. The pressure there might be atmospheric again, and it shoots out into the room. All right? The reverse, if you want to make water convert its kinetic energy into pressure potential energy, again, work on the horizontal level, so you're not playing with the gravitational. You want the water, which it has lots of kinetic energy, to slow down. When it slows down, it converts its kinetic energy into pressure potential energy. How do you do this? How do you make it slow down? Well, one way, and I muddled around with it last time, is to shoot it into a wall. It will slow down right at the center of its flow, and that will be a point where it has converted its kinetic energy into pressure potential energy. But technically the fancy way of doing this is by using the opposite of a nozzle. A nozzle is a narrowing in a pipe. You take a pipe along and then you neck it down to a narrow pipe and it squirts through at high speed. If you do the reverse, you take the flow through at high speed and you put it into an anti-nozzle, or what's called a diffuser. It spreads out and gets wider. The air slows down as it goes through that diffuser, and its pressure increases. And many of you are familiar with diffusers because they're common attachments for hair dryers. You buy a diffuser, they're sold as diffusers. Is the name familiar to people? What's the point of this? Its job is, sometimes with a hair dryer, you don't want high-speed air at atmospheric pressure, which is what comes out of a normal hair dryer. It's coming out with no pressure to speak of, but it's traveling really fast. And if you want the windswept look in your hair, you want it all go out sideways, yeah, use high-speed air. It'll, unless you have hair piece, in which case you have no hair. If you put a diffuser on a hair dryer, that slows the air down and its pressure rises. And you might think, well, it was already coming out at atmospheric pressure. If you have the pressure rise, it comes out at higher than atmospheric pressure. The diffuser actually then affects the hair dryer in an interesting way. The pressure inside the pipe of the hair dryer is below atmospheric pressure. And the story for this will come to sort of later on. When you put a diffuser on a hair dryer, you are actually causing the flow of air in what used to be the nozzle to be below atmospheric. It's a partial vacuum in there. If you're desperate for a vacuum cleaner, you can drill a hole in there and you can go vacuum stuff up because it will be below atmospheric pressure. But when it goes through the diffuser then, it slows down, its pressure rises back to atmospheric pressure, and the value of this finally is that it is not coming out at 30 or 50 miles an hour on your hair. You're not drying your hair with a hurricane. And for certain circumstances, that's a good thing. Okay? So a nozzle necks down and the fluid speeds up. A diffuser necks outward and the fluid slows down and its pressure rises. I should say it with a nozzle. When you neck down, the pressure drops and the kinetic energy and speed increase. In an anti-nozzle or a diffuser, the kinetic energy or speed drop and the pressure increases. All right? And these all have practical purposes, and they're all over the place. And if you start looking for them, you will find them. Having talked so much about it, let me show you these guys in action. And the first version of this which I'm going to show over here, is this guy. Actually, before I even do that, there's another demonstration that I keep forgetting to show you, which is also associated with Bernoulli's equation to an extent. It's the idea that if you have water that's high and water that's low, the water, rather than attribute it to Bernoulli's equation, let's just look at it from the perspective of everything accelerates in the direction that reduces its total potential energy as quickly as possible. Remember this old observation that it applies to objects. Why does a chair, why does this bottle, when I tip it away from its stable equilibrium, why does it go back? We could do that in terms of torques and forces, and it would drive us nuts for a while. But we could also just look at, well, when I tip it like this, its total potential energy, which is essentially only gravitational potential energy, increases. It's a little higher on average than it used to be, a little more altitude. And it accelerates in the direction that reduces its total potential energy as quickly as possible. Remember that idea? These funny looking little vases here, it's called Pascal's vase or vases. Pascal being the origin of the Blaise Pascal, philosopher. You know, these the people way back then, alas, they were all white males, but that's whatever. They're not entirely true with it, but the exceptions are all interesting, but I can't solve cultural disasters. So these vases, Pascal's vases, they're all connected at the bottom. So this black pipe here is actually hollow, and they all share the same bottom. And the point is, if I pour water into one of them, if it fills up, it's going to have a lot of extra gravitational potential energy. It could get rid of that by transferring the water could transfer into the other vases. So what you're seeing is I fill this one, being the only one I can aim well enough to hit. The other ones fill to exactly the same level. So there's the expression, water seeks its level. If you fill a bathtub with water, the water doesn't stay on the side with a spigot. It spreads out, getting rid of gravitational potential energy, until it's dead flat in the absence of wind or something, or you splashing. So the water level here is the same in every one. It's just trying to minimize its total potential energy. It's another stable equilibrium. If I disturb it away from this equilibrium, give it a slosh, it oscillates. You can see it oscillating. It's trying to settle back at that equilibrium. It's got all the inertia effects and the restoring forces. The whole thing's there. Okay? Fun and Games 1. Fun and Games 2, not this tub here, but this guy here. This is a water tank. It's just water, okay? It's connected at its bottom through a hose to a nozzle. All right? Nozzle's currently covered. I'll uncover the nozzle. And the point here is this has all the features I just talked about, all the energy exchanges. Right now, there's no energy in the water. The water's at low level. It's motionless. Its pressure is basically atmospheric, and it's down low. It's in terrible shape. No energy. I'm going to plug the hose here for a second. I'm doing work. I'm adding energy to the water. It's like half a liter of water, and it now has a lot more energy per half liter than it used to. If I now let it flow, I'm used to making a mess because I like making messes. All right, let's tip this more upward. There we go. Okay. The water is undergoing all the transformations. Gravitational, and descends through a pipe of constant cross-section, so it's becoming pressure potential energy. Back up a little bit to become a little bit more gravitational. Then it goes through a nozzle where it becomes kinetic. Then it rises up in open air, so it's converting kinetic into gravitational. Oh, we ran out of water. Refill. It's got to work its way through to get all the air bubbles out of the way. Okay, so now it's kinetic here, so it went pressure to kinetic to gravitational to kinetic, and if I let it hit my hand, it is converting kinetic into pressure potential energy and pushing on my hand. Okay, so all 6 conversions are occurring here. Questions about them happening here? You hopefully noticed that the height of the water here is close, but it's not quite the full height of the tank it started with. The energy per drop, there's an air bubble here. I gotta get the air bubble out because it causes trouble. Oh. The air bubble's working its way up, and did you get out? No. Anyway, more water. I should get one of those yellow signs, slippery. That would surely protect me against any liability. Until somebody trips over the sign and sues for having an obstacle. Okay, so now the water, you'll notice, goes from this height where all of its energy is gravitational, down, now all its energy is pressure. Now a little bit of gravitational, but mostly pressure, to mostly kinetic, to mostly gravitational, to mostly kinetic. The height of this is pretty close to that, and it depends on that. It never goes higher than it started from. Woo! Right? So you can see not only is the energy going from one form to the other, but you can see it's conserved. That is, it can't go higher than it started from because it doesn't have the energy go higher than where it started from. Is everybody okay with that? Well, how about if we go higher? Like, I wonder what this hose is attached to. Oh! Well, the energy in that water was installed before class by Al. And it's coming over here. As the water descends through this pipe, which it's not doing yet, but it will in a minute, as it descends through this pipe, its pressure increases. So the pressure down here has increased significantly. It's descended farther than over there. The pressure here is something like half of an atmosphere of pressure. Again, 1 atmosphere of pressure is just a conventional unit that's about 100,000 pascals. So it goes down through the pipe, up. Its max pressure is about there. Now it's coming back up, and it's losing a little bit of pressure in exchange for gravitational. Then it goes through the nozzle, and again, it can't rise higher than it started. It's pretty messy. I'll stop before we become a trip hazard. But you can see the higher the water tank is, or the water tower is, the more pressure you have down here, the more kinetic energy you can end up with per drop. Any questions about those? All right. So, what to say about water distribution? A few odds and ends before I move on to talk about garden watering. That is, distributing water is complicated. The energy is going from, yeah, okay. Thank you. In a town that's mostly horizontal and has very short houses, life is relatively simple. But if the water needs to go up and down any distance, you have to be careful, because if it goes down a considerable distance through the plumbing, the pressure will go up dramatically. If it goes up any distance without some assistance, its pressure will drop dramatically. So things like skyscrapers, they have complicated water systems installed. Some of you are architects, and building a tall building, you have to prepare in advance for the fact that getting the water to the 18th floor or the 50th floor is going to require pumping. Otherwise, there's going to be no pressure left. The water's going to rise to a maximum height, having converted all of its pressure potential energy from the water company into gravitational. It might only get to the 10th floor, and that's it. It's done. It won't go any higher unless you lift it. You have to add energy to it. So skyscrapers have pump systems in them to carry the water to higher levels. They have pressure regulators along the way to make sure that the water coming out of your shower, for example, didn't arrive there at 1,000 pounds per square inch, which is sort of a pressure washing pressure. Right? You don't want a shower that's like that, right? it'll remove a little too much skin. So they have to control the pressure. There are things like if you're trying to fight fires on the 20th floor of a tall building, getting the water up there and getting enough energy in it to get it up there is problematic. So that a lot of those buildings have essentially water towers in them. And if there's a fire, they will move water deliberately as high up in the building as possible to invest energy into it, so that it's a lot easier to work with high energy water than low energy water. It's all familiar? Yeah, okay. I'll stop with water distribution. Well, one last thought is that lifting and lowering water is one thing. Lifting and lowering sewage is another. It follows the same rules by and large. And so there are pumps, believe it or not, moving sewage around. If the sewage came into the system in the valley, it has to be pumped up over the hill. So there are pumps for this. And where you start hearing about the pumps and stuff are things like flushable wipes of various sort. Flushable. There's been some just read about flushable wipes. Yes, they're flushable in the same way that golf balls are flushable. I mean, you can get them to go down the toilet. Do you want them down there? Not really. And so some of these things that go down into the system are not very compatible with the pumps that need to move the sewage around. All right. If you need a PhD thesis project topic, you can work on that. All right, garden watering. So up until now, I've been treating the water as something that's sort of, the fluids, they're mostly sitting still, or we're moving them through things. Now I'm going to start looking at water and fluids in general as sort of a real entity of their own, that sort of have a life of their own. They can do things even when there are no solids around. You don't need a balloon to see that there's air. You don't need plumbing to make water do interesting things. You can actually have pure fluid systems that are interesting. And so my demonstration of that for a long time has been this. So just a plastic pail with a hole cut in the bottom and a flexible, pliable lid here, and we put rubber bands in so that if I pull the lid back and let go, the flexible lid gets pushed forward, right? So if I do this, nothing interesting seems to happen. But I have a smoke generator up here. Okay, so now it's full of smoke. Oh, come on. There we go. You see the... Whew. Why weren't they going at first? That was pretty strange. Where's the button? These are vortex rings, also known as smoke rings. And you can feel them when they hit you. Sometimes I get them to sit up in the ceiling, you sort of watch them sit there, spin until they slow down and do nothing. So just sort of sit there spinning. Yeah, it's pulling through. That's what's going on. The rubber diaphragm is on its last legs. Anyhow, what's happening with these vortex rings is as they go through the hole, as they go through the hole, they're rubbing against the hole, and they slow down there, and they start to curl. And they curl, and they spread out, and they curl so that they're swirling. Each ring is swirling. Its outside is coming back toward me. Its inside is going forward. And it crawls its way through the air, heading forward. Obviously, it's pretty intact, and its central core is the same air. It's not exchanging with. It's not like a wave where the wave here is made of local water and the wave there is local water. This guy's actually moving. The smoke actually moved forward. Some of the people in the department were trying to duplicate this with air rings underwater. They were trying to blow these in the AFC by sinking to the bottom of the pool and making the bubbles go up. It's a long story with it, but they got in terrible trouble because they did not like people under the water, like holding their breath and stuff and just hanging out down low. Long story. But okay, so the point of showing you this is air in air sort of having a life of its own. There's those structures flew along entirely built out of fluids, highlighted by smoke, but otherwise it's all fluids. All right, and there are lots of examples of other things, systems where fluids and the world of fluids is really interesting. And we'll look at some of them, or try to. All right, so garden watering. The first thing I'll do is I'll ask this question. Let's see whether I can manage to get far enough along to do this. We're sort of toward the end, but you've all seen this story. If you open a hose of any sort, wide open, and you start setting water through it, the water goes through it. It may come from what seems like a very high pressure source, like the water company delivers water at about 6 or 7 atmospheres of pressure, however you measure atmospheres. So it's considerably above atmospheric pressure. How much? By about a factor of 5 or 6 over ordinary pressure. And yet when you open a faucet or hose, typically the water comes out not all that fast and at atmospheric pressure. Where did all the energy and pressure and stuff go? And a way in which you see this is a wide open hose, the water comes out kind of not very fast, but if you put your thumb over the hose, it comes out like crazy. And I guess I can just show you, it's not a big surprise. So here's water coming out. Good. Okay. That water started as very high energy water back at the water company. The water company pumped on that hard. And yet it's coming out low, not much gravitational, slow, not much kinetic, atmospheric pressure, not much pressure, nothing. It's all gone. What's going on? On the other hand, if I put my finger over it, I can spray. You guys are in trouble, right? I can spray you if I want. If I don't want to get in trouble. All right. What happened? So the question is, when of these two situations do you get more water out? When I'm just letting it flow as a gentle stream, or when I put my thumb over it and blast it at high spray speed? When's more water coming out? How many think that more water comes out when the end's open and the water's coming out gently? How many think more water's coming out when you put your thumb over it? Okay, a handful are going for when your thumb's over it. But most of you are going for when it's open. The answer is when it's open. That's when more water comes out. If you try to fill a container with that water, you'll fill it faster with the open hose. And that's not a coincidence. The reason for that is when you let the water flow through the open hose, it travels finally as fast as it can through the hose. It's using the pressure imbalance between atmospheric pressure here, where it's delivering the water, and back at the water company, where the water company is pumping. There's a difference in pressure, right? And that pressure difference pushes the water forward. If water were simply inertial and no rubbing, nothing like that, the water would accelerate to quite a high speed when it came out the end. That pressure difference associated with a certain mass of water would cause a certain acceleration, and finally the water would pick up a certain speed. But it doesn't do that. The water rubs its way along through the hose. It does experience friction-like effects. And those friction-like effects get worse the faster it goes. This is different from dynamic sliding friction. Sliding friction it pushes the same hardness on a sliding box, whether the box is sliding fast or slow. Water, that's not true. Water rubs more when it's going fast than when it's going slow. So the water rubs like crazy when it's going fast through the hose, when the hose is open. It loses all of its energy en route to thermal energy. When you pinch off the hose, however, you slow the water's flow through the pipe. So you get less water per minute. You can't fill a container as fast. But the water doesn't rub as badly. It doesn't waste as much of its energy as thermal energy. And all the energy remains there. The energy per drop makes it all the way to your thumb, where it becomes kinetic energy as it goes through the nozzle your thumb forms with the pipe. So what you're doing really is you're shifting from the world of a lot of friction and energy waste to the simple world I described earlier today, where the water essentially flows perfectly. And the pinching off allows the water to show almost its perfect flow. All right, well, I'll do it more detail on Wednesday.